One of the most important tools we have in studying physics mathematically is the idea of vectors. And today I want to tell a little story about vector equations, both in terms of pictures, the arrows on a page, and telling it in terms of coordinate systems and components. The example I'm going to use is a very simple equation, a vector plus 2 times b vector equals c vector. And I'm going to first tell that story with just the pictures, with the arrows themselves, because that's a big part of how I, as a physics person, think about vectors. So what's that equation mean? It's a left-hand side equal to a right-hand side, and the left-hand side is a sum of vectors. Vector sums, when you're adding two vectors, you add them head to tail. So this left-hand side, a plus 2b, tells me that I start at the tail of a, and I follow it to its tip, and then I'm adding 2b. One way of thinking about that is that I'm taking the b vector, which is down 2 and over 1. I'm taking the b vector and adding it in, and then I'm adding it again, 2 times b, right? There's my b. So a plus 2b is the a vector plus 2 times the b vector. Now, an even more general way of thinking about 2 times the b vector is to say start with vector b and multiply its length by 2 without changing its direction. 2 times b is just stretching the vector out to be twice as long. That's an even better way of thinking about it, really, but it's nice to see that doing 2 copies of b does the job. So a plus 2b gets me to this point. An equal sign is a comparison of two vectors, and when you compare vectors, you place them tail to tail. In this case, what that means is I start at the same place that I did for a plus 2b. I start at the same tail, and the right-hand side is just vector c. And you can see that vector c, when I follow it, it lands me at the same place that a plus 2b did. That means they're equal as vectors. Same starting point, same ending point, they're equal as vectors. So this is a visual representation of that equation as arrows on a board or arrows on a page. Now what I want to do is talk about how we make sense of this in components and in a particular coordinate system. And we're going to do this in a couple ways. So I'm going to start with this in the most simple form. I'm going to say, I'm going to figure out what the components of each one of these three vectors is. Vector A, you can see here on the board, I've labeled my x and y directions. I'm going to go ahead and write vectors as 3 component vectors because we live in a 3-dimensional world. All the z components are going to be 0, so that's kind of a waste of space. But I like to have that 3-component thing because it makes me feel familiar. It's a nice way of doing it. So my a vector then, when I write down the components of my a vector, I'm going to write it as a column of numbers, a column vector of numbers. So what are these? What are the components? The x component from the tail to the tip, tail to head, is positive 3. The y component from tail to tip is positive 2. And of course, there's no z component to my a vector. That's vector A in this story. Vector B, if I look at vector B, again, I'm going to look from tail to tip, so it helps to place it at the origin, place the tail at the origin. Vector B, I'm going to put this down here for reasons that will become clear later on. Vector B, as a 3-component vector, has x component from tail to tip. I'm moving to the left, which is my negative x direction, so it's negative 1. My y component appears to be downward, which is my negative y direction, so negative 2, 0 is my b vector. And my c vector, and again, for reasons to be seen later, I'm going to write this down over here. My c vector, as a 3-component object, my x component from tail to tip is plus 1. There are no units in this, by the way. My y component is negative 2, 0. As a physics person, I'd really prefer to have units with my vectors, but I'm doing this as a very general thing, and the units should just distract from the story I want to tell today. So, okay, I've got these 3 vectors in components, and the beauty of this vector equation is that when I write it down, I can write down that vector equation, write down these components as I go, and get my equation. So let me just write them down. I've got, writing this down in components, I've got 3, 2, 0 plus 2 times my b vector in components is -1, -2, 0. And I can add that up. I can do this calculation. That's equal to 3. So I'll write it out. This is 3 plus 2 times -1. This is 2 plus 2 times -2. And 0 plus 2 times 0. When I add that all up, 3 plus 2 times -1, that's 3 minus 2, that's 1. 2 plus 2 times -2, 2 minus 4 is -2, and that's all just 0. And that is my c vector. Check! Yay! That's exactly what I had over here for my c vector. So you can see the components add up. Basically, I just added across the x components, with the 2 distributing in each part, added across the y components, added across the z components to get my final answer. It's nice to see that work out. It's nice to see that adds up and these components all work. This is in the coordinate system that I've described here, with x being straight to the right and y being upward. Now, the interesting thing about vectors, about true vectors in space in physics, that distinguishes them from, I don't know, a list of zip codes vertically, or a list of just random data in a vertical list. The thing that distinguishes a vector in space from just a list of data is that if we rotate to a different coordinate system, vector equations still hold, and so the vectors themselves the components will all adjust to match that new coordinate system. Now, there are lots of ways of doing this, but I want to do a very visual one right now. And to do that, I'm going to take a minute and work out A, B, and C as vectors, not just in components, but as a magnitude and a direction. So for example, for vector A, I know that vector A has components 3, 2, and 0. I'll ignore the 0 for this point. So the magnitude of vector A, its absolute value, its length, I find by doing the Pythagorean theorem. And I had actually meant to do this on the next line down, hadn't I? Let me put a picture on this side. Let me draw a picture over here just to have my vector A. So here's my vector A as the hypotenuse of a right triangle whose legs are in the x and the y direction. And so this leg is 3 and this is 2. Then the magnitude of vector A is the square root of 3 squared plus 2 squared plus 0 squared. I add up all 3 squared, all 3 components squared. And what is that? It's 9 plus 4, the square root of 13, which is about, square root of 13, I worked this out, 3.61. 3.61. Okay, so that's my magnitude of vector A. You can see where that comes from. I can also work out the angle of vector A, because the tangent, if I call this angle theta A, I can say that the tangent of theta A is the opposite side over the adjacent side, those lengths. It's a right triangle, I can draw that. And so opposite is 2, adjacent is 3. So theta A is, the inverse tangent of 2/3. And when I work that out, I get that this is about 33.7 degrees. That's what I can do just doing a right triangle to relate the components of A to its magnitude and direction. I'll do the same thing for vector B. Let me draw a little picture again. My usual thing, draw my picture. Here's vector B as the hypotenuse. And I'm going to draw lines parallel to the y and x axes. So they're perpendicular, parallel to x and y. And my components on these sides, I guess this side is my -2, and this side is my -1, right? And so I can go through and I can say, same questions. What's the magnitude of B? Well, the magnitude of B is going to be the square root of -1 squared plus -2 squared plus 0 squared equals, well again, -1 squared is +1. -2 squared is +4, so this is the square root of 5, which is about 2.24. 2.24 is that. And same story, which angle do I want to do today? Let me do this angle here. this angle, if I call that theta b, the angle for vector b, then tangent of theta b is going to be opposite over adjacent. And when I draw one of these right triangles, I've actually drawn a right triangle. What I really want to do is the length of the sides, not the plus or minus for the vector component. So this is, tangent is opposite over adjacent. My opposite side length is the absolute value of minus 1 divided the absolute value of minus 2. The length of that side is the absolute value of minus 2. So that's just 1/2. So I can solve to find that theta b is the inverse tangent of 1/2, which is about, I have this down somewhere, 26.6 degrees. That's my angle there for angle theta b that I've drawn. Same thing for vector c. In this one, I can actually do some shortcuts, right? Let me draw it out first, just so I have the drawing. Here's my vector c. And I can draw a little right triangle with legs parallel to x and y, as usual. I could have drawn this one too, right? I mean, it doesn't matter which one I draw. Parallel to x and y could be either way. I could choose any angle I want. I'll choose this angle. Call it theta c. And to do this, I guess I've got my 1 here and my minus 2 here. So to find the magnitude of c, again, magnitude of c is going to be the square root of 1 squared plus minus 2 squared, which is another square root of 5, or about 2.24. And my tangent of theta b, or theta c, tangent of theta c is going to be opposite over adjacent. Remember, absolute values, since I've drawn this, I just care about the lengths, not the plus or minus for the components. Absolute value of 1 is opposite, divided by the absolute value of negative 2 is 1/2. So theta c, it's inverse tangent of 1/2 again. It's going to be, so inverse tangent of 1/2 is, again, about 26.6 degrees. So I now know magnitude and direction for each of these. The reason I did that, partly it's just interesting to see how you go from vector components to magnitudes and directions, but the reason I did it was this. I want to introduce a new, different coordinate system. I sometimes in physics will find situations where I want to have coordinates that are aligned with one of the vectors in the problem. Maybe it's an unknown. Maybe there's something about it that makes it special, where I want to line up my coordinates with that vector. In this case, let's say I want to choose a coordinate system that's aligned with vector c. So instead of x being to the right and y being up, I have the freedom to choose anything I want. I'm going to choose this to be my new y-axis. I'm going to choose this thing right here to be my brand new y direction for my coordinates, for my problem. Here we are, trying to get it kind of straight so it looks reasonable for you. Okay, good enough, good enough. Here's what I'm going to do. I'm going to draw this y-axis. There we are. That's my y-axis, and this is going to be my plus y direction. I could call it y prime or something. I don't want to confuse with weird labels. That's my new y-axis. My new lined up with c. I deliberately chose it to be lined up with vector c. Now, let me choose a tilted x-axis that's perpendicular to this one. You can work it out. If this was 2 down and 1 over, this should be 2 over and 1 up. If I work this out, if I get my axis right, 2 and 1, something like it, I'll see what I can do, see how close I come to getting this right. It's going to look something like this. Does that look pretty close to perpendicular? That's pretty close to perpendicular in my eyes. So this is my new x-axis. So I've got this x-axis. What do I do with it? Well, okay, my claim is, and this is the power of vectors, my claim is that the equation a plus 2b equals c should still hold in these new coordinates. But to figure that out, to figure out what those components are, I'm going to need to work out some things about the components in the new coordinates, because it's not just 3, 2, 0 anymore for a, because a is almost entirely along the x-axis. What's it going to look like? Let me come over here and figure that out. I didn't draw this long enough. I should have drawn this a little bit longer, because what I need to do to find the components of a, I need a right triangle where a is the hypotenuse. So a is the hypotenuse of a right triangle, but the legs of the triangle have to be parallel to x and parallel to y in my new tilted coordinates. So I can draw a triangle where that's the hypotenuse, that's one leg, and perpendicular to it, parallel to the y direction at that angle, I can drop a y-axis down from here, the line parallel to y down from here, give myself a right triangle. You see my triangle now? Here it is. Leg, A vector as the hypotenuse. That's my new right triangle for A. Now, to be able to do any calculations, I need to know some things about angles inside. Just like here, I had my theta A, right? I need to know what the angle is between the A vector and my new x-axis. That's going to be this dinky little angle here. That's what I care about, right? This dinky little angle. Well, what do I know? I know that this angle here, how do I want to draw it? This whole big angle here, from there to there, was my 33.7 degree angle. And if I just tilted my coordinates to match vector C, well, I drew in here my theta C, this angle was my 26.6 degrees. That's what this angle was. I tilted the whole thing by 26.6 degrees. That means that this little angle here, if I tilted the y-axis over by 26.6, I must have tilted the x-axis up by 26.6. And suddenly you can compare these. You could say, I've got 33.7 up to A, 26.6 up to the new x-axis. Left over in this little slot here, what's that going to be? The difference. Looks like it is 7.1 degrees. I'm going to have some rounding error here. That's okay, I'll deal with it. But I've got 7.1 degrees as my angle that A is above my new tilted x-axis. So let me work backward now and work out the new components of A, because the components are not 3, 2, 0 anymore, because I'm much farther than 3 along x, and I'm certainly not 2 up from x. So let me work out what those new components are going to look like. I'm going to have a very similar sort of thing going on over here. But just in reverse. Same story, but in reverse. So what do I get? My new A vector components. A, well, I can look at it. My x component of A, it's in the positive x direction. So it's definitely a positive number. I just erased my magnitude. I was not supposed to erase my magnitude for A. I wrote it down. That's good. So what is this x component? That's adjacent to my 7.1 degrees, right? So I know, let me write it down here, I know that the cosine of 7.1 degrees, that's my 7.1 degree angle here. Remember, my right triangle has a leg that's adjacent to that going along the tilted x-axis. Cosine is adjacent over hypotenuse, right? So it's going to be my x component, I'll call it AX, in my new coordinate system, divided by the magnitude of A. Or in other words, AX over, what was it? Magnitude is 3.61. Cosine of 7.1 degrees is going to be a number I can look up somewhere. I don't know it off the top of my head, but I can plug it into something. So if I want to know what my x component is, it's going to be in the positive direction. It's going to be the magnitude, 3.61, the magnitude of A, times the cosine of 7.1 degrees. Similarly, my y direction, my y component for A, looks like A is still in the positive y direction. So I'm going to put a plus here. Y, that y component is opposite my 7.1 degree angle. So sine of 7.1 degrees should be equal to AY divided by the magnitude of A. And so by the same token, I can multiply by that magnitude, positive 3.61 times the sine of 7.1 degrees. My z component is still 0. So I've got this. When I plug in those numbers, you can put this into a calculator and get it. What I end up getting is, as 3 components, this is 3.58, almost the full 3.61. It's almost the full length to the right. And 0.45, much smaller than the full magnitude, much smaller than the 2, and 0. So those are the components of A calculated in this tilted coordinate system. You can see it works. Mostly x, a tiny bit y in this tilted coordinate system. What do I get for b? I want to tell the same story for b. And let me do that. Same story for b. Look at b. Look at the components. Again, I probably should have kept some of that, but hopefully you've got it written down. I certainly have it written down. For b, again, I look at the picture. I know, what do I know? I know that I've got this was tilted 26.6 degrees, so I know this is tilted down 26.6 degrees. What else do I know? I know for B, I knew that this angle here, this angle in that crack was also 26.6 degrees, right? 26.6 degrees, because it was the same angle over, just the other direction. B and C are just mirror images of each other, sort of, that way. So that was also 26.6. Well, hey, that's supposed to be a 6, really. So this I calculated. This dip down was because I tilted all the coordinates by the same amount. And so what's left over? What is this angle going to be? Just for example, that's a place I can look for this. That angle, when I work it out, I figure out that this, there's some rounding stuff going on here that I think may be a little bit iffy. Let me just plug it in. So this is 26.6, 26.6, and this have to add up to 90 degrees. If I plug that into a calculator, I thought I had this written down somewhere, but if I plug that into a calculator, I can just work it out. Let me do a quick little check here. Use the calculator on my phone, why not? I get 90 minus 2 times 26.6. I get 36.8 degrees for that angle. It turns out when I'd done this a bit more carefully, I got 36.9 degrees with the rounding error. So I'm going to go ahead and say 36.9 degrees. But it adds up, if you keep some extra digits, these will all round off to be the right thing. So that's my angle here, 36.9. Why do I care about that angle? Because I'm going to do another right triangle. From here, this is my hypotenuse again. The b vector is going to be my hypotenuse. And I want to turn it into a right triangle where one of the legs is the x or the y axis. Let me just do that right. Oh, I could have done those and added them. That would have been clever too. Let me do that right here. Here's my x-axis coming over. I can send a parallel to the y-axis going down like this. And give myself a right angle there. I have my 36.9 degree angle in here. And I can start working out components. So my x component is the component along my tilted x-axis. It's going to be negative. I can see it's going to be negative. And just as I did with A, what I'm going to do, it's going to be, that's going to be the related cosine of 36.9. So magnitude times cosine will be that component, just like it was up here. And it's negative, my magnitude here was 2.24 times the cosine of 36.9 degrees. And here, for the opposite side, that's going to be just like it was up here. This is in a negative direction, but otherwise, because this is opposite that side, it's related to sine. And so this is going to be 2.24 times the sine of 36.9 degrees. And down here, 0. And having done that, I've actually worked out those numbers elsewhere. Oh, that's not a very good equal sign. Equals, I worked out just plug it into a calculator, get these numbers, and you'll get minus 1.79 and minus 1.34 and 0 for those 3 terms in this equation, and for those 3 terms in this vector. Those are the components I get for B. Same thing for C. Probably, but C is actually the easiest of all in these coordinates because remember, we chose our coordinates to line up with C. So C's coordinates are actually the easy ones. C vector, I can just read off of the picture. The x component of C in the tilted coordinates is 0. I chose it to have 0 x component. The y component, it's in a negative y direction, negative y, in these tilted coordinates I've defined. And it's the full length of C, the full negative 2.24. and then 0z as usual. That's my c vector. This looks like a mess now. I've got all these things, I've rounded them off, but I've got all these things. It looks like a real mess. But let's look back at our vector equation. And maybe I need a tiny bit more room here just to put this together. Let me put in a step. Let me write down what my vector equation is going to be. My vector A in this new tilted coordinate system is approximately 3.58, 0.450 plus 2 times vector B minus 1.79 minus 1.340. If I do that, what do I get? Well, if I do it, 2 times 1.79 is going to be 2, 7, 14, so 3.4, 3.58. But negative, it works. So this is, I'll put the equals down here, equals 3.58 minus 2 times 1.79. Well, basically say plus 2 times negative 1.79. This is 0.45 plus 2 times minus 1.34, and this is 0. So what is that? That top one really is just 0. The next one, 2 times 1.34 is 2.68, plus 0.45, 2.23, so minus 2.230. You can see that's almost exactly equal to C. Off in the last decimal place, but that's just that rounding error. The last decimal place often you'll be a little off in the calculation like this. It matches though. Even in these funny tilted coordinates, we tilted the coordinates, and when we tilted them, we had to change the components of each one. Zip codes, a list of zip codes would not have changed just because we tilted our map a little bit, but the coordinate components have to for a real vector. But they all changed in a way they combined to give a perfect match, well, nearly perfect match, setting up all of our equations, coming up to show that the vector components still add up to match. Even though the components are all different, the equation itself still holds. That's an example of doing a vector calculation, the type of thing that comes up all over the place in physics, and seeing that your components always add up right no matter what coordinate system you happen to choose. I hope that's useful, and I hope this can be a good example for other vector things you might need to do in the future.